Yeah, this is with my amazing collaborators here. Brandon was mentioned a couple of times today, and this is the Federated Learning team at Google. I'm going to talk about what's called auditing for differential private mechanisms. And I have to admit that I do not know much about crypto, and the talk itself has not much to do with crypto. My goal is that maybe I can explain to you what this maybe small facet of a problem that people in differential privacy care about, so that maybe you can spark some connections and collaborations with the crypto community. So let's get started. So this starts with a very common problem when you're implementing differential privacy, which is kind of like the following. So when this paper dropped on arXiv about a year ago, those of us who were working on differential privacy got quite surprised, because if you look at what they claim, the state-of-the-art DPSGD algorithm, which I think by now you're familiar with given the previous talks. So it's differentially private stochastic gradient descent algorithm to train a model on MNIST. So if you want to get accuracy of 98.1%, then you have to pay in privacy of epsilon around 3. So the best epsilon you can get is around 3. The smaller, the more private; bigger, the less private. And what this paper claimed is that by changing a little bit on what's called clipping, just a little bit, they could achieve better accuracy with epsilon that's 40 times smaller. So it's 40 times better privacy with a very small change. And it turns out that after a few weeks, they released their code and people looked into it. And what happens is that they made a very small mistake in the implementation, and very honest mistake. And it goes as follows. If you're doing DPSGD, what you do is you train your model, weight WT+1, by updating it, by taking a step negative of your gradient with a step size eta. So you average your gradients, and each one needs to be clipped, which was mentioned many times, which means that the norm of the gradient has to be bounded by something. I'm just putting one there as a reference. And then you take the average, and you add a noise that's tailored for the epsilon and delta that you're shooting for, which is privacy, so you don't have to care about it. But the important thing is that it's 1 over the size of the mini batch B that you scale it with, because that's the sensitivity of this query. Meaning if you change one gradient arbitrarily, how much does the gradient update change is, because the norm is bounded 1, it's 1 over the size of the mini batch B, which in this example that they were running was 4,000. Okay? So the noise has to be scaling like 1 over B. And the mistake they made was that they normalized the gradient before clipping, not after clipping. So they moved this 1 over B inside the clipping. What it means is that now, if you change one gradient, how much you can change this update is 1, not 1 over 4,000. But the noise they were adding was still scaling like 1 over 4,000. So they were adding 4,000 times smaller noise by the small honest mistake. Hence, they can get arbitrary epsilon they wanted to. So this is kind of common problem in privacy, which means that if you make a mistake in differential private algorithm, typically you do better. So it's very hard to, or it's less incentivized to find and fix such bugs. So what a relatively new line of privacy research is focusing on is called auditing for differential privacy, which was really studied back in 2018 with this award-winning paper by Dan Kiefer and his group, which is that, well, in this example, you had a code, you had a line-by-line order, you had the actual implementation of the code, but oftentimes you might not. So given a black box access to a privacy mechanism, can we detect violation of the claimed privacy by maybe sampling multiple times from the output of the mechanism and somehow figuring out whether it's violating the privacy or not? So that's called auditing. And it's quite active line of research these days. And concretely, this is how it's going to work. So as per the definition of differential privacy, which I'll go back to in a bit, But how you do it is that you create two databases. One is called the null. We're gonna call it null hypothesis for the reasons that will be clear in a bit, which is the ambient data set that you care about. In our experiment, we use fashion and mist. And the other one is the same thing, but has one more data point, which is called canary. And it's specially constructed by you to serve your purpose that you will learn in a bit. And given two databases that change only in one data point, on this side of the privacy barrier, what you do is you choose one of the data set without telling the other side, and then you train a model according to the DP mechanism in question that you care about. And then you only pass the trained model to the other side. And what the other side, as an auditor, what you're doing is that you're only given the access to the output of the mechanism, which in this case is trained model parameters. And then you're trying to run a binary hypothesis testing on whether it was trained on the data that was with canary or without canary. So the question is, was the canary there or not? And how well or how accurately you can answer this question determines how private your mechanism is. So you run this many times, measure your accuracy, and that's gonna determine whether you're violating your claim DP or not. So that's the underlying standard procedure. And now I'm gonna go deeper into how concretely this auditing is done in 3 steps. And the main reason I'm going so detailed is that we are gonna make innovations on each of these 3 steps so that we get a better auditing algorithm. So here we go. It starts from the step 1, which is the definition of differential privacy, which you've seen multiple times today, which is you're given 2 data sets, D0 and D1, that differ only in 1 entry, and you're given some output region R, or your decision rule, such that probability that a differentially private, let's say training mechanism A, outputs a model that's within some region R should be not too different from when it was trained the one with canary or the one without canary. And how different it can be is measured by the value epsilon and delta, which measures your privacy leakage or your differential privacy. So smaller epsilon and delta means that those probabilities are similar, so they're more private because we get a plausible deniability that the canary can claim, well, I was not in the data set, it was the algorithm, and that gives you plausible deniability. And I'm gonna do something here, which is that this is the standard definition where the left-hand side, you can view the decision region R as the region where you claim that canary was there, then bringing the terminology from statistics and binary hypothesis testing, that's the probability you claim the canary was there when it was trained with the data set with canary, so it's true positive rate. And the other one is the probability that you claim canary was there when it was trained on the data without the canary, so it's false positive rate. So this gives you some linear constraints on what your true positive rate and false positive rate can be. And you can draw this on 2-dimensional plane where x-axis is the false positive rate, y-axis is true positive rate. And this linear condition gives you a line, one of these red lines, where it's shifted by delta and slope is e to the epsilon. And the symmetrized version of it gives you another line, and altogether it defines this pentagon region. And this graphical view of differential privacy has much deeper meaning related to other things like amplification and composition, which we won't go into in this talk. In this talk, I'm just using it to make clear what we're doing in auditing. It's going to make it much easier to follow. And when we say a particular mechanism A is epsilon delta differentially private, what it means is that for any choice of the evidence or triplets, the data sets D0, D1, and the decision rule R, it's going to give us a particular false positive rate and true positive rate the mechanism achieves, which is the blue point there, and take the union over all data set pairs and all decision rules, then that gives the gray region, which is the achievable region of this mechanism. If the whole region is inside this red pentagon, then you claim this is epsilon delta differentially private. And if it's outside, it's violating it. So that's the definition of differential privacy I want you to remember, because this is going to be important throughout. And when you're saying you want to audit a particular mechanism A, what it means is that you're suspecting that the region of this particular mechanism you want to audit is outside the epsilon delta pentagon claimed by the mechanism. And when you say you're auditing, what you need to do is you need to find a counterexample, which is a pair of data sets, D0 and D1, and accompanied decision rule R, such that it sits outside of this red pentagon. Then you've successfully refuted the claim of epsilon delta dp of this mechanism. Yep. Clear enough? Right. So when you're actually doing auditing, what are you doing is that you are trying to find this evidence D0, D1, and R. And within the standard recipe that I explained earlier, it means that you need to design a canary example that's strong, that stands out, so you can, with high true positive rate, find it or find its evidence. So if you do that, if you have strong canaries and strong decision rule, then your true positive rate will be higher because you can find it easier, and your false positive rate will be smaller. So the point will move up and left, which means it's easier to refute the claim. Whereas if you use the weaker evidences, it'll be inside the pentagon and hard to refute the privacy claim. And typically, what people use to find the canary or the decision rule is the loss of the trained model on either data sets of the canary example. If the loss is small, then you claim probably the canary was in the training data. And if loss is larger than the threshold, you claim it's not in the training data. And that's the kind of common recipe that people use. That's the second step of designing these counterexamples. And the third step is that even if you decided on our canary and the decision rule, you don't get to see that blue point because you don't know all the probability or randomness involved. You only see it through examples. What it means is that you need to evaluate the true positive rate, false positive rate. In this case, probability that you are below a threshold and probability you are above the threshold, or you're below threshold on either data sets. But what we get is a Bernoulli distribution with such biases, which tells you on one sampled instance of one training, you get a model and you evaluate the loss, and it's either above or below. It's a 0-1 Bernoulli distribution. So now you are asked, given this Bernoulli distribution samples, how can you estimate the Bernoulli bias, which is as old as, I don't know how long you have to go back to do this, but it's like hundreds of years old. So how you do it is you take the empirical mean, because that's what you're trying to estimate from this Bernoulli distribution. But because you want high confidence bound or high confidence solution, what you do is you add the confidence interval, which scales like roughly 1/square root of n if you have n training models or n samples to do this. You do it for one for false positive rate, one for true positive rate, which gives you, put them together, a confidence square or confidence rectangle. And you give yourself a benefit of, or is it benefit of doubt or the other way? And you take the most private point is the bottom right point of the square. And even if even that point is outside this epsilon delta rectangle, the red one, then you know with whatever the confidence you build the confidence interval with, that you've successfully refuted the claimed epsilon delta dp of this mechanism. So that's what it means to audit a differential private mechanism using the standard recipe that people have came up with. Any questions so far here? Okay. It gets a bit more complex for here, so I hope I got everyone until this far. So my goal is to get everyone until this far, and then it depends on how familiar you're with DP afterwards. But this is the overall framework just one more time. You got two data sets. This is what you do in your auditing, null, and then alternative hypothesis. You train n models, getting n samples from this Bernoulli distribution. You take the average and put a confidence interval that you know how to. They give you a confidence square. You put it on this two-dimensional plane. And then if the whole square is outside of the epsilon delta pentagon that you were asked to refute or prove, then you've successfully refuted the claimed privacy. Otherwise, you declare you don't know. Okay? And two, I think, important notes I want to make is that if you somehow make the canary stronger so that it's easier to detect the presence of the canary, then the whole square will move to the up and to the left, making it easy to refute. Another control you have is if you run more trials so that n is larger, if you train many more models and average more instances, then your confidence interval is going to go down, so the whole square becomes smaller, which is another way you make this auditing easier or more stronger. So this is what people did, exactly what I told you, on the example that had a mistake in their code that I showed you in the first couple of slides. And if you plot the loss, we said we're going to make a decision based on the loss of the model output on the canary for the case where it had the canary in and didn't have canary in, you get this kind of two histograms. And when you're doing auditing, you cut somewhere that's your threshold, and you use on this side of the threshold that's shown there to compute the true positive and false positive and do this. And the reason I'm showing you this is that this was done at Google by other people, not me. But they trained how many models? 200,000 models to do this. And typically, you don't get to train 200,000 models in your life. So how can we? Okay, one thing we need to understand is why do we need so many models to do this? But also, more importantly, we want to come up with ways you can do it without training 200,000 models. Maybe you can refute the same kind of violations. So one of the reasons why model auditing or privacy auditing is so difficult is the following. And this might be a little bit subtle for people who don't know, who's not familiar with differential privacy. So let me try to go slow. So if a mechanism violates, let's say, differential privacy, and these plots are drawn from actual data. I didn't hand draw them. This is like drawn from the actual distributions that I'm showing up there. So I'm showing you a mechanism called randomized response, which is a simple mechanism that outputs only 0 or 1. That claims 0.8 dp when the actual dp is 2.0. It's just chosen so that it looks good. Then the violation, the actual mechanism looks like this gray region. So it's going to be easy to find some bugs that fits in the gray region and refute this. But in reality, in practice, most of the mechanisms are much more complex, and almost all of them are relying on the Gaussian mechanism where you add Gaussian noise, which is not that complex. The real things are much more complex. But even that simple Gaussian mechanism, if you look at the same claim DP and same actual DP, then the region you get looks like this. So this violates this one only in this little corner. So if you zoom in, this violates a little bit here. And when you say you're auditing a Gaussian mechanism, what you're saying is that I'm going to find an evidence here, and I'm going to make a confidence square that's small enough that it will be actually outside this red region, which is really hard. And that's why you need so many samples, and it's hard to audit in practice. But nevertheless, let's try to get better at auditing differential privacy mechanisms. Okay. I hope I didn't lose everyone on this slide. But this is just telling you why it's difficult. You don't have to know this to understand what we do. So what we do is a simple idea. We want to inject k canaries instead of a single canary at every time you train a model, so that if you have k canaries, then you can test for k canaries and average them over. In the best world, in the ideal world, you will get a gain of factor 1 over k in the variance, or factor 1 over root k in the confidence interval. Let's try this. And the main key ingredient, it turns out, is the randomization. So you do have to use randomized canaries. I'll get to that in a bit, what it means, to achieve the full benefit of adding multiple canaries, because other people tried without randomization and have failed. And this is how they fail, which is a bit, again, subtle. So what people tried with determinist canaries is that, well, instead of adding one canary, I'll add k canaries. So I have two databases. One is the same as before. The other one has k canaries. And I'm going to train models on it. I'm going to test my canary on all of them. And as my test statistic, instead of a single canary, I'm going to average over k canaries presence or absence, which hopefully this is variance smaller by 1 over k. And maybe I can get a confidence interval that's better by 1 over root k. And this doesn't make sense for DP person. And the reason is that those two data sets are differing by k samples. So to be precise, they are supposed to be k times more private, not epsilon delta private, but roughly what's called group privacy, which is roughly k epsilon and k delta more private than two databases that change one single canary. So what it means from the auditing perspective is, here is an example scenario how they fail if you use deterministic canaries. So let's say you're auditing some randomized response and you ran it with some number of samples and your confidence score was too large. It overlaps with this epsilon delta red pentagon, so you don't know what's going on. So you said, okay, now I have this much budget. I cannot get more samples, but I can run it again with more canaries. So if you do that, and one way you can do it is you can add the same canary, let's say twice, so that your detection will be stronger. And what it means is that the whole square will now move up and then left, because you added the same canary twice. It's going to be easier to detect it. But what you need to refute against is now not just epsilon delta dp, but actually k epsilon and k delta dp, where this red pentagon follows you up there. So it's hard to get any gain by using these strategies. Another strategy is, well, I'm going to then add two canaries that are completely independent, very different, so that my square goes down. Then it's true that your square will be maybe √2 times smaller, so you get a smaller square. But where it is doesn't change, because you're still just refuting one canary at a time. But again, you have two canaries in there that's different between these two data sets. So the privacy you're trying to refute against is now k epsilon and k delta. Gets bigger and doesn't give you any gain. So how do we get around this problem is the main fundamental question we're asking, which is, how can we exploit the presence of k canaries without suffering from this kind of group privacy? And the answer is you need to randomize your design. And before I tell you what we do, let me just show you what we get. So I didn't tell you what we do, but this is what we can get. So if you're auditing as a toy example of proof of concept, the Gaussian mechanism, which means that you're going to sum up a bunch of vectors, which each one is no one or less, and then you're going to add appropriate Gaussian so that it's 2.0 differentially private, and you're trying to audit this, right? Maybe they claimed 0.5 dp. Then in auditing, what you do is every point in this plane, what it means is that you got your models trained n times, and you got your confidence interval and plot it on the plane, and then you fit the tightest epsilon pentagon that you can fit, and that gives you the tightest lower bound you can get using your experiment, and that's what's shown on the y-axis. So it's a lower bound on the true epsilon, so the larger the better. The more trials you do, the smaller the square gets, so the steeper the slope gets, so the higher the lower bound gets. And what I want to show you is the difference between one canary, which is the standard auditing that we now know, compared to the orange, which is the K-canary example, which is the auditing that we propose. I didn't tell you what it is, but roughly speaking, if you're auditing for something like 0.7 dp, then you get about 4x gain. And if you're auditing for 0.8 dp, you get around 16x gain. So that's the kind of gain you can expect or you can get using our algorithm. That many less samples needed to refute the same level of privacy. So we are gonna innovate on every step of the 3 steps of standard auditing. And this is how it works. We start from the definition of DP. And it's gonna look, even to the experts of DP, this is gonna look like I didn't do anything, which is fair, but I did something, which is the following. So if you look at the definition, it's almost identical, with only one caveat, which is the P in the probability is a joint distribution of the 2 databases, D0 and D1. So I'm allowing you to choose databases also randomly, as long as the probability is taken care of in the probability. And what it does for me as an auditor is it allows me to design randomized canaries, and that's gonna make all the differences. So this we call lifted DP because we're lifting everything to the randomized databases. Up to that, everything is the same. If the mechanism had a particular gray region it was achieving with the original DP, the lifted DP region would be exactly the same. If whatever we're testing for the pentagon had original DP had a shape, had a particular shape, it's exactly the same on the lifted DP, which makes us allows us to use this instead of the original DP. Now that we are equipped with using randomized canaries, we want to do the following in the second step of canary design or the experiment design, which we call leave one out construction. But first, I'm gonna show you a deterministic canary version of leave one out construction and tell you why it fails so that you understand why we need a randomized canary. So if you're using deterministic canaries to do this auditing, what I'm saying I'm gonna do with leave one out construction is that I'm gonna add K canaries here, call it my alternate hypothesis. And my null hypothesis, I'm gonna test it against K null hypotheses, each one leaving one of the canaries out, so that each pair is still one hop away or one canary different. So I'm still checking for one, or definition of DP. But this doesn't really give you any sample reuse or sample gain, because if you want to get test statistics from such pairs, this one you can reuse K times, right? You can train one model from this and test for K, canary 1 there, canary 2, canary 3, that's fine. So you get K times gain for reusing this. But the null hypothesis, you don't get any gain because each null hypothesis, you have to test for whatever is missing, which gives you one statistic. So I really didn't do anything, and you don't get any gain. It costs you as much. But what's gonna save you is that if you randomize this design, everything changes. And it goes as follows. So what we propose is that you do this experiment, but you make sure that one data set has K canaries randomly drawn from the same distribution, IID, independently and identically distributed. That means that the whole alternative hypothesis is now not a database, but a randomized version of the database. The sub is a random quantity. And for the null, you do the same thing, but with K minus 1, canaries drawn as such, then you can couple them so that they are always one canary different. But because all of them are coming from the same distribution, from the perspective of checking for lifted DP conditions, doesn't matter which one you call what. What it means is that you can use this to test for the K canaries that are in there. And you can use this to test for any number of canaries drawn from the same distribution that is freshly drawn. Because it didn't matter which one you call what, due to the symmetry of the design and exchangeability, which I won't go into the details here. But at the end, what you can do is you can train one model from either one, and then test for many hypotheses, and make this rigorous and precise throughout, due to randomization. How am I doing on time? How much time have I got? 5 minutes?
Yeah, well, actually even more, like 10 minutes.
Okay, 10 minutes should do. Right, so this is how our proposed auditing works. So you decide on how your canary is gonna be generated, distribution, and then at the beginning, you're gonna run it n times, but every time you're gonna generate k randomized canaries and generate one database which has k minus one of them, the other one which has k of them. And then you train two models based on this k canary and k minus one canary data sets. And then for the k one, which is alternative hypothesis, you test for the k canaries that were in there. And the other one, for the null hypothesis, you can test for, I wrote it as k here, but really it can be any number. You can be 2k, 100k, it doesn't matter. You can test for any number of canaries drawn fresh, so that they're not in the data set, but it's coming from the same distribution. And you do it n times. And for now, let's just set this to k so that the notations are a little bit simpler. Then you're getting k statistics from every training you do, and that's what you get. So to recap, the first step, we went to lifted DP so that we are allowed to use randomized canaries. Second step, we went for leave one out construction so that we don't have to pay for group privacy, but we are allowed to reuse samples in these tests. And what we're saying is that instead of checking for DP condition like this, each time we run a test, we get roughly k test statistics where we're averaging over, such that we get square root of k gain in the confidence interval is the goal. But can we do it? It's not clear because these k statistics are correlated to each other. So what we really need to do in the third step, how do we get the confidence interval, is that we need to measure how correlated these statistics that came from the same trained model are, in order to take care of uncorrelation of those. And what it means is the following. If we don't use any other information, you only get 1 over root n confidence interval as before. Sorry. Okay, thank you. But if you go and measure the second order statistics, meaning the relation between two of these k canaries, you can measure the correlation. It's a number between 0 and 1. And if that happened to be small, then you get a extra 1 over k. If this one was 0, then you get 1 over k. In the confidence interval, it shrinks by a factor of 1 over root k. If the correlation is large, it means that your experiment was or design was wrong, and you don't get any gain. In the best case, when the correlation is at most scaling like 1 over k, with the k is the number of canaries you put in there, then you get a gain of confidence interval that's 1 over root nk instead of 1 over root n. So this is the experiment I showed you earlier on Gaussian mechanism, which is the same thing. running our algorithm. And the question is, how uncorrelated are the canaries such that we're getting this gain? So we can go ahead and measure the correlation, which is number between 0 and 1, as we increase the number of canaries. And you can see that the correlation actually decreases like 1/k in this Gaussian example, as we were hoping it would. But you cannot keep increasing number of canaries, because what's shown here is roughly that green star is the lower bound you get with a particular number of canaries that you're adding. So you get a better lower bound, means higher lower bound, until a certain point around k equals square root of n, which is kind of predicted by theory. And then afterwards, it hurts you, because too many canary means that there are too many randomness, and it hurts you. And there is a way of interpreting it as a bias variance trade-off, where the variance gets smaller and smaller with canaries. This is the orange up there. Going up is kind of smaller because it's a lower bound. And bias is kind of starts to hurt us when k increases. This is just to tell you that we cannot indefinitely increase k. There is a sweet spot, and our theory tells you it's around root n, and in practice, it works well with root n. N is the number of trials that you're running. The question that I didn't address so far is that what we do is just give you a recipe you can use to reduce this confidence interval so that you get tighter lower bounds. But how do we design particular canary for particular application that you care about is what other people do. And how other people propose to design their strong canaries, we can take that and apply to our setting, which is what I'm going to show you in the next couple of minutes. And this is one example where people said that, well, a strong canary C is, instead of manipulating the data, you actually go and manipulate the gradient, because from the DP, differential privacy perspective, you should still be differentially private. So people propose that canary itself will be a gradient, that whenever the gradient is accessed in the DPSGD, you return the canary instead of the gradient. And in the end, you try to detect it by taking the model parameter at the whatever time step you want to run it, take the inner product with the canary itself. And if the inner product is large, maybe the canary was in there. If it's small, maybe the canary was not. And that's what people propose as a strong canary. And if you want to use this idea, but do it in our setting, which the canary has to be randomized, what you do is, you add k canaries drawn perhaps randomly from the sphere of whatever the radius that you are going to use. And you draw random canaries. And we did this. This is how you lift your canary design to our setting. If you do that, the lower bound you get, higher the better, because it's a lower bound. As the number of trials gets larger, with k canaries, you get the orange, and with one canary, you get the blue line. So that's the gain you get in the lower bound on the epsilon parameter that you want a lower bound on. And as a number of canaries, usually square root n, which is the dotted line, that's the square root of n, seems to be a reasonable, robust choice. And another example, one last example that people proposed as a strong canary design might be, well, you design a single canary, that's what people did, as the following. This was for fashion and needs. You look at the images and you take them as a vector and look at the PCA of those vectors, and there'll be a direction where they're not changing much, right? That's where there's least information. You take that as your image, okay, whatever is least changing, and then you put a label that's least likely, and that's going to be my canary. So you're trying to find the canary that's most unlike typical fashion in this data set. And that's what people proposed. And how do we lift it to our setting is that, well, instead of taking the bottom of the PCA, you take something like the bottom 300 dimensions, and then randomly pick your canary in the 300 dimensional subspace, and call that your image. And the label, you can put whatever, that's most unlikely. You do this, and the gain is, again, similar. The blue is one canary design, exactly, designed as I said. Orange is the K canary design, as I told you. And again, K equals root 10 seems to be a robust and reasonable choice. Yeah, so this is an active research area with a lot of interesting results. We only touch on the one aspect, which is how to get better confidence intervals, but there are many, many related questions related to how do you design strong canaries? What happens in the federated setting? Can you do it with even smaller number of trials? So this is a very exciting research area. I invite you to look at it and try to bring your own ideas. And yeah, our papers is online. Thank you for your attention.
We have time for a quick question. Questions?
Yeah, very nice talk. I have like one general question is, because I guess DP like what requires like the worst case guarantee, right? So yeah, it's very interesting. So if we can create some ID example and we show, okay, you didn't satisfy this guarantee, and so we say the DP guarantee is broken. But even if you pass this test, whether we can like what can we say about like the actual DP guarantee we can ensure?
Right, that's a good question. So you can never use it to pass an algorithm because DP is for the worst case. But at the same time, I think how people in DP are viewing these approaches is that you could design the D naught also, which we didn't, right? And the reason people don't is that they actually want to know what the kind of the holy grail is. You train one model that you're going to use and use that model to understand the privacy aspects of that model. That's what you want, right? By the end of the day, you don't really care if the algorithm was whatever epsilon dp. You want to know if your model was epsilon dp or not, which was trained on the data set that you care about. So in that sense, it's more complicated. It's not just about refuting algorithms' claim dp as I was explaining it, which how academics view it. It's more about understanding how private your algorithm is. In that sense, we're using the data set that's not optimized over as a worst case, and hoping that maybe it's not just a lower bound, but more about a more kind of like an approximate actual DP. So that's the hope, but mathematically that's not true. Yeah.
Yeah, one other short question is, what's the higher order correlation? You mean like a second moment I can guess is covariance, but
right.
What's a higher order?
So random vector we get is 0, 1 vector of k dimensions. Correlation between any pair of them is second order. 3 or 4 of them is higher order. Using higher order, you can potentially do even better than this. Everything is with second order. I didn't show you those results. Empirically, they're not that good.
Yeah, thank you so much.
Thank you.
Thank you again.
One more question.
We don't have time for one more question. Let's take it offline. Sorry.
I'll be around.
Yeah, let's do it offline because there's a schedule. All right. So, well, maybe you can ask while the speaker is coming up. Come back, ask the question. Where's the next speaker? Oh, this is the last one. We don't have one more speaker because it's listed here. Then go ahead and ask the question.
Thank you. So I guess my question is that, do you think that DP audit is useful in the case where I'm like dealing with some randomized algorithm, which I cannot formally analyze, like satisfy some form of DP guarantee because it's not standard like as adding Gaussian noise, but I suspect that it will provide some DP guarantee. So can we use DP audit to actually prove that this randomized algorithm will give you some privacy guarantee?
So as I said, mathematically proving it will be close to impossible because you need to maximize over D0, D1, and R, which we didn't do here. We just designed one and do it. So for one, you can do it, which means that it gives you a lower bound. For an upper bound, you have to maximize it, which there's no way of doing it. Like it's impossible, you cannot maximize. But we are hoping that all this gives you a sense of how private your algorithm is, so that in an ideal world, you can use this. So if you have a particular algorithm A and particular algorithm B, then you can use this framework. It'll give you some epsilon different lower bounds. And in an ideal world, the lower bounds, the order of it will be the same as perhaps the actual DP, theoretical DP guarantee, which you may or may not know. But these are not mathematical, but empirical. And perhaps, that's good enough for practical applications, where we don't even know what epsilon means anyways.
Okay, thank you.
Thank you.
So
So does this approach work black box if you have a model that is trained on streaming data over time?
Oh. Well, as long as there is a DP-like condition you're checking, it works generally for anything, including not just DP, RDP, FDP, and other things, for those of you who know it. And I don't see why anything should change with streaming data as long as you define it correctly. So what we do is very kind of modular to everything else that's going on. It's not particularly for DP, really. It's just checking for these things. So I believe it can be. So that's my answer.
all right, so I thought there was one more talk, but there isn't. So thank you everyone for sticking to the very bitter end and listening to this wonderful talk. And thank you for the speaker again.
Thank the organizers for a wonderful workshop too. Thank you.